Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu, and today we're going to talk about many electron atoms, and we are officially entering chapter 8. We talk about, in previous chapters, we talk about some quantum numbers. So now we're going to have one step further to include the 4 quantum numbers altogether to you. So let's take a look at this. We already know the principal quantum number and the angular momentum L, magnetic quantum number and sub L. And in this chapter, we'll focus on the spin quantum number and sub S. So it has 2 permitted values, positive half or negative half, that corresponding to the direction of electron spin in an orbital. So for electrons, they move freely in an orbital, but also it can have some self-spins. They have 2 different directions of spins, clockwise, counterclockwise, or we usually talk to them as spin up and spin down. Okay, so that up and down corresponding to either positive half or negative half. Now, for each electron in an atom, we have this 4 quantum numbers to describe the electron. The first 3 describe which electron orbital this electron sits, and also the final spin quantum number defines the direction of electron spin in the orbital. So each electron in the orbital is described by these 4 quantum numbers. And also we have the Pauli exclusion principle. So this principle says there's no 2 electrons in the same atom that have the same 4 quantum numbers. That defines the maximum electrons we can have in a group of orbitals or in one orbital, right? Because no 2 electrons in the same atom have the same 4 quantum numbers. That actually means in each orbital, we can only hold 2 electrons, one spin up and one spin down. As students, you are required to know, or you are expect to be able to calculate the maximum electrons in an orbital or in a group of orbitals. Usually we look at the magnetic number, integers from negative L to positive L, right? So I listed a table here telling you or summarizing the number of orbitals in S, P, D, and F orbitals. So in S orbital, we can only have NL equals to 0, and that we total have 1 value, 1 orbital. So maximum we can have 2 electrons. For P orbitals, we have 3 different orbitals corresponding to M sub L equals to -1, 0, and 1. So for these 3 orbitals, we can maximum have 6 electrons. The same with D orbital, we have 5 orbitals, and that maximum can hold 10 electrons. And for F orbitals, there are 7 different types. So in total, 14 electrons in all of the F orbitals. Now we know different types of orbitals. Now we are going to move on to the multi-electron system, an atom with multiple electrons. And there are a few things we need to talk about. So first is called effective nuclear charge. And that's under the big umbrella that we are talking about these electron-electron interactions, or the how these electrons behave in the atom. The interplay of nuclear attraction, electron repulsions, and orbital shape leads to phenomena in many electron atoms. So when we say phenomena, basically we refers to different energy levels of these electrons. Okay, so according to Coulomb's law, higher charge interacts more strongly than lower charge. And also, if these 2 charges are closer to each other, the interaction are stronger. So a higher nuclear charge Z, uppercase Z or Z, that means we have more protons and more charge in the nucleus. If we have more of those, that increase the nuclear electron attractions. They are different charges, right? Positive in nucleus, negative in electrons. They are attracted to each other. So higher charge in nucleus will increase this attraction between nucleus and electrons, and thus lowers the sub-level energy. In other words, stabilizes the atom. The lower the energy, the more stable it is. Okay, so let's take a look at a few pictures. If we have helium plus as 1s, the electron filling the 1s orbital, and also we have lithium 2 plus. In both cases, we have only 1 electrons. They're sitting in the same electron orbitals, but because lithium 2 plus has 2 more positive charge in the nucleus, there are stronger attraction between the nucleus and electron in the lithium 2 plus case. Okay. However, we're not only looking at this 1 electron system, now we're really moving on to the multi-electron system. So if we look at the atom, helium atom and lithium atom, both of them have multiple electrons. For helium, we have 2 electrons. For lithium, we have 3 electrons. So this actually will complicate the situation as we are having extra electrons in the system. So then the electron have repulsion. They both carry negative charge, or all of them carry negative charge. They have repulsion, and that repulsion have another name called shielding or screening of the electrons. It is the repulsion from other electrons to reduce the full nuclear charge. So because it's the repulsion, this electron overall will experience or feels less attraction from the nucleus. So, and that is due to another electron, and it's called shielding. Of course, the shielding reduces the nuclear charge it feels, and the felt nuclear charge of an electron is called the effective nuclear charge, Z subscript EFF. Okay, across a periodic table, the effective nuclear charge increases from left to right, and also shielding effect decreases from left to right. We will talk more about the training in periodic table in later videos in this chapter. Okay, so besides shielding, we also have another effect electron can have, and that's more related to the orbital the electron sits in. That is called penetration. Okay, so now we have a diagram. The Y is the radial probability, and the X is how far away the orbital is from the nucleus. We have 1s orbital, which is most closer to the nucleus, and then 2s and 2p orbitals. For the 2s orbital, you will notice there is a nod. So which means at this nodding point, there's no way for anyone to find an electron there. The possibility of electron to show up there is 0. But before the nod and after nod, we have a probability to see 2s electrons show up in those areas. So in this diagram, the 2s has 2 peaks, while the 2p orbital has only 1 peak, and the major peak of the 2p orbital is a slightly left, or it sits in between of the peaks of the 2s orbitals. Okay, by looking at this diagram, an electron in 2s orbitals spends part of this time penetrating very close to nucleus. We're focusing on the first peak you see here in the 2s orbital. And that electron of the 2s actually penetrate through the 2p and show up closer to the nucleus, and this is called the penetration effect. Penetration has 2 effects. First, it increases the nuclear attraction for 2s electron over that for 2p electron. So because it gets closer to the nucleus, right? It feels more nuclear attraction. And second, it decreases the shielding of a 2s electron by the 1s electron. 1s is inside, like in general, it's closer to the nucleus than 2s. But because of this penetration, some portion of the 2s electrons, or some likelihood of the 2s electrons getting closer to the nucleus, and then it kind of offsets the shielding from the 1s. It feels stronger attraction and less repulsion of the 1s. So the penetration decreases shielding of the 2s electron. It not only happens with 2s and 2p, and here another example shows the 3d and 4s. For 4s orbital, you can see here there are 3 nodes. And again, for the first peak of the 4s orbital, it penetrates really closer to the nucleus, penetrates through the 3d orbitals. So still here, you can see the penetration effect. All of the concepts we talk about in this video, shielding, penetration, the effective nuclear charge, all together contribute to different energy levels of different energies of sublevels. So SPD orbitals have different energies because of these effects. And in general, within the same quantum number, with the same principal quantum number, S orbital has less energy than P orbital, which is less than D, and then less than F. So SPDF in terms of energy increase, and also we say S orbital is the most stable one, then P and D, and then F. All right, this is the end of this video, and I'll see you next time.